lesson of the course. And I'm just going to open it up here. It's called normal approximation of the binomial distribution. So we're going to be using the z-score and the techniques for continuous probability scenarios, and we're going to apply it, like the Unit 6 concepts, we're going to apply to the Unit 5 type of scenarios for binomial probability. So this top part just is kind of trying to get us to remember or decide why we are going to use Unit 6 techniques on Unit 5 concepts. So consider a coin is tossed 50 times. What is the probability of getting 30 heads? So we always start by saying, let X represent the number of heads flipped. So our point of interest here is flipping a head when a coin is tossed. And we say, okay, well, if they're talking specifically about 30 heads, I'm going to set random variable X equal 30, and I'm using my formula for binomial distribution because we're talking about a Bernoulli trial that one flip is not going to affect the next flip's likelihood. They're independent events, and I'm grouping it into success or failure, where this time our point of interest is flipping a heads. So flipping head is our likelihood of success, which is 0.5. So it's n choose x 50, because there's 50 opportunities to flip that head. 50 choose 3 multiplied by 0.5, the likelihood of flipping a head raised to the 30, n, and then multiplied by q, which is also the likelihood of flipping the tail, so that's 0.5, to the n minus x, which is 20. 50 minus 30 is 20. So I put that all into my calculator, and I came out with 4% likelihood. So that's just Unit 5 concepts. But when the question slightly shifts to at least 30 heads, then the question becomes quite difficult and tedious. So what is the probability of getting at least 30 heads? Well, then we'd be opening up many different cases that would satisfy getting at least 30 heads, because the solution to this problem would involve the likelihood of getting 30 heads, or 31 heads, or 32 heads, or 33 heads, or 34 heads, all the way up to 50 heads. And that would be crazy, time-consuming. Maybe not if we used Excel, but the way around that is to use today's lesson, and that is using the normally distributed characteristics on to the binomial distribution. It's called normal approximation to the binomial distribution. So to simplify calculations of this type, we can approximate the probability using the normal distribution. The binomial distribution arises in situations of independent repeated trials in which the outcome of each trial is either a success or a failure, Bernoulli trials, and a graphical representation of a binomial distribution with n equals 15 and p equals 0.4 would look like this. So it really depends on the scenario that we're given if we're allowed to use the normal approximation. And if we had a scenario where there were 15 trials and the likelihood of success is 0.4, then we'd end up with a probability distribution that is shaped like a bell or normally distributed. In this case, yes, we could use the normal approximation, and indeed there's some rules that can help us to decide whether we can use it or not. So this says, notice the bell shape of the distribution. This suggests that we can approximate a binomial distribution by a normal distribution. So we're using Unit 6 concepts onto Unit 5 scenarios. And so here are the formulas, and one of them you should really recognize. Here's the formula for our mean x bar, which is going to be n times p. Our standard deviation is going to be the square root of the product of n times p times q, remembering that if you're just given what p is, you can always figure out what q is because it's a binomial situation of success or failure. And then this one here you should recognize, which is just our same old z-score formula, the observation minus the mean divided by the standard deviation. So these approximations, we're allowed to use these three formulas, are considered to be reasonable if p is close to a half and n is fairly large. The further p is from a half, the larger n should be to compensate and still maintain a good approximation, right? These kind of rules and ideas are making sure that the graph would indeed be normally distributed or in this like bell-shaped curve. The general rule of thumb is that a normal approximation to the binomial distribution is acceptable if both n times p and n times q are at least 5. So that's going to be one of the steps in our solutions. We always have to check that the normal approximation is allowed to be used. And so down here, these are some diagrams that show different n's and p's. So this one, we would not be allowed to use the normal approximation techniques. This one, we would also not be able to because both of them are skewed graphs, right? Skewed left, then skewed right. This one, yes, we give a check mark. It looks like a bell-shaped curve. So let's take a look down here. There's one other thing that we need to consider, which is taking the binomial whole numbers and switching them over, translating them onto a continuous scale where decimal numbers make sense. So one final consideration is the need to account for approximating a discrete outcome experiment with continuous distribution. This is done by treating each outcome as a unit interval. For example, 5 is no longer 5, it's 4.5 to 5.5 in the successes in a normal distribution. So probabilities such as random variable x being less than and equal to 5 would be approximated by random variable x being less than and equal to 5.5 because 5 turns into the interval of 4.5 to 5.5, and if this is less than and equal to, we want to count everything that represents 5, which on its interval we would include 5.5. And then also if random variable x is equal to 7, in the binomial sense, 7 is then interpreted as 6.5 to 7.5 if we're using normal approximation, and because it's just equal to, we would use both of those values within our z-score calculation. Okay, so examples. We'll see that when we get to our only example that we'll do as a group. Check to see if each binomial distribution can be approximated by a normal distribution. So we've got n is equal to 10, p is equal to 3. So I'm going to go in here and just do a quick calculation of what q is, right? It's 1 take away the likelihood of success. So that would be 0.7. And then I'm going to say, all right, n times p is 10 times 0.3. All right, that's 3. Already we're a no, right? The n times p and the n times q have to be at least 5. So this is unnecessary, but I'm just going to go through it for thoroughness. This would be 7. This would be good. So since this is a no, this would be no, not high enough. We can't use normal approximation on this first one. And then on the second one, right, q would be 1 take away 0.45, which is 0.55, and then I'll just go on to the side and go n times p is 14 times 0.45. Okay, so what's that? 14 times 0.45, that's 6.3. That's good to go. And then n times q, that's 14 times 0.55. 14 times 0.55 is 7.7. That's also at least 5. So yes, we can use it in this scenario. Okay, now let's get into an example. So calculate the probability that in 100 rolls of a die, a 6 will appear between, move that, 10 and 20 times. Okay, and I'm going to say that this is inclusive. So we're including 10, we're including 20. Step 1, check to see if we can use the normal approximation. Like even before this step 1, I'm thinking Yeah, this makes sense. I'm rolling a dice. My first outcome on the dice is not going to affect my second outcome. I want 6 to happen, so rolling a 6 is the success. They're independent Bernoulli trials. So, and it would be very difficult to go between 10 and 20. I'd have to do the formula 10 times and then add them all up. So we're going to use normal approximation. So my first step is to go n times p, which is 100 rolls times the 6. So the likelihood of rolling a 6 is 1 out of 6. So it's 0.17. It's like repeated or whatever. So I'll just keep all the numbers. And that's 16.7. That's going to keep going. And so that's good enough to go. And then n times q is going to be 100 times, and that's 1 minus 0.17. So I'm going to go, that was 1 out of 6, 1 minus that answer. So I'm going 100 times 0.83. That keeps going. So I'm at 83.3 repeated. Okay, so that's good to go too, right? Because it's at least 5. So now I'm going to use my formulas. I'm allowed to use normal approximation for this scenario. So I'm going to say x bar is equal to, and that was just our regular, actually, let me just look up one sec. My formulas that we're going to use are these ones. Right, so x bar is equal to n times p, and standard deviation is equal to the square root of n times p times q. Okay, so x bar is equal to n times p, which we've already done up here. So it was like 16.6 repeated, or 0.7. And then my standard deviation is the square root of n times p times q. That would be 100 times 1 out of 6 times 5 out of 6. I'm just going to use the fractions here so I don't lose too much accuracy. So it's like saying 100, in my calculator, I could go 100 times 1 times 5, because all the numerators together is 500, divided by 36. And so I get 13.8 repeated on my calculator, and I'm going to take the square root of that. So my standard deviation for the normal approximation is going to be 3.73. And the last thing here is, this step 2 just said to calculate the mean and the standard deviation, which I did. And now I'm going to come down here and it says find the z-score relating to the appropriate values. So we nature, we've got to make like a translation. So if it was discrete, we were talking about random variable x being less than and equal to 20 and greater than and equal to 10. So we want to roll that 6 between 10 and 20 times inclusive of 10 and 20. But now 10 isn't 10, but is 9.5 to 10.5. Okay, and so if we want to include 10, we got to choose the lower boundary of what 10 represents. And then if 20, in the discrete world of things, it becomes 19.5 to 20.5. And so since we want to include 20, we're going with the upper boundary of that little range. So when it goes to coming up with z-scores and finding their percentiles, because we're looking for likelihoods of occurrence here, I need to come up with 2 z-scores. My first z-score is going to be equal to, the formula is x minus x bar over standard deviation. I've got 9.5 being my observation, and I'm subtracting my x bar, which is 16.7, let's say, I'll just round to the 1 decimal, divided by 3.73. Okay, so that is going to be negative 1.93. I got to look that up and then come up with its percentile. So negative 1.93 going up. I got to pass a couple of lessons there. Negative 1 point, okay, so I've got to go to the negative. There's a negative 1.9. Here's 1.9, negative 1.9. And then 3. This would be 0, 1, 2, 3. So I'm at 0.0268. 0.0268. 0.0268 for my first percentile. And I'm going to go down, write that guy down. Where is it here? Okay, so I am going to write that down. My percentile for that first z-score is equal to 0.0268, and I'm going to do it again for my second z-score, which is going to be the upper boundary of 20. So I'm going 20.5 minus that mean divided by the standard deviation. Okay, so just calculating that, I get 1.02. That I got to look up, and I got to come up with the percentile. I'll just write look up and percentile 1.02. So I'm going up. 1.02, it's positive, 1.02, 1.0012, it's going to be 0.8461. 0.8461. All right, so we're going back down and writing that value down. So my percentile, just going to fill in right here, is equal to 0.8461. Step 4 says find the corresponding z-score values. I think I already did that. And then it says determine the probability. So let me just see. Find the z-score relating to the appropriate values. You know what? This probably should have said find the corresponding percentiles, which I just did right here. So percentile 1 is 0.0268, percentile 2 is 0.8461. And to come up with the probability, I'll just draw a little picture here, right? If this is my 0, which goes in the center, negative 1.93 has a percentile of, about 3%. And then my higher z-score is 1.02, right? And this percentile is going down here at about 84% or 85%. And so to get the likelihood or the percent of the data set that's in between, we just have to subtract the smaller percentile from the higher percentile. So my final answer, the probability that random variable x, actually, I'm going to do that a little slightly different. I've got to do a little range here. That x is less than or equal to 20 and greater than or equal to 10, right? That's considering it's discrete. It's going to be 0.8461, take away 0.0268. And I'll just put that into my little calculator there. 0.8461 minus 0.0268 is 82%. So 8193. And that would be my final answer. Okay, so similar to what we've been doing this since lesson 2, I'd say, but applying it to Unit 5 concepts. So as a final answer, there's an 82% chance of rolling a 6 between 10 10 and 20 times when we roll the dice 50 times. Or no, 100 times, it said. So what I'm going to do with this last example here, you guys can do that one on your own and then check it within the completed notes. Okay, so after that, you can do the homework for this section and then prepare yourself for tomorrow's test. Okay, have a great day. Bye.